Evening, everyone. You had a good weekend. Most of you got A's on the test. What a shock. Something new I discovered today. I'm trying to do my Math 30 grades, and if students are missing an exam, like let's say a Math 30 person took 4 exams and didn't take the 5th exam. Well, it's reporting that their grade is something out of 200 points, but then when I go to like submit the grades, it switches it back to out of the whole thing. So it's like Canvas can't communicate with itself. So what I've done is I went through our class, and this only applied to one of you. Only one of you had missed one of the assignments. So what I did is I put, as long as I enter a 0 in there instead of just leaving it, then it'll be a more accurate representation of your scores. But it doesn't really apply that much to you guys, because as I said, you guys have, with the exception of one person, everybody's turned in every exam.
Professor.
Mm-hmm.
I think that person is me, because the first exam, you said we would have like a little extra time to submit it, like by the end of the night, and I sent it through Canvas, and I did the test, but I have a 0 for the test. It was Chapter 7 test.
Yeah, it's the first exam. And when I'm on I don't know, I'm not going to be able to look right now, because I'm actually in Canvas doing this, and I'd have to leave this to open up the thing. Either that or I'm too stupid to figure it out. But I don't remember seeing anything on Canvas from my point of view.
Yeah,
I get a to-do list on the side, and grade this exam, that exam. So I haven't seen that, but I'll look next time. Okay.
Should I send like another message with the exam attached? Because I sent it through the Canvas message. I didn't submit it through like the submission.
Maybe that was the problem. So do that.
Well, the submission had closed, which is why I didn't submit it.
Oh, then email it. So then scan it and email it to me.
Scan it and email it. Okay.
Yeah, I have a girl in the 030 class, and I mean, it wasn't until the 5th test that she figured out how to submit, and she was having all kinds of technology issues. I don't know, but anyway. All right. So,
hey, Bobby.
Yeah.
Did you decide which day this week we're not having class? Sorry,
Thursday.
Okay, thanks.
Yeah, I've got stuff I got to deal with this week at some point. So I thought Thursday would be the best day, but now I've got other shit that I got to deal with. All right, so here we are, and you were the last class, so no more this. So 185 Taylor series. Okay. Now, just as we did last week, I want to review, go over some stuff again, and make sure that we're all at least. Where's my draw button? Draw. Okay, so let's do the quick review. So we have a series. Sum of the ANs, okay, and we want to know whether or not it converges or not, okay, and so we developed several tests. We had the integral test was the first one. Now, but at this point, if AN is f of n, then what we do is we look at the integral from 1 to infinity, or some number to infinity, of f of x dx. Okay, and the conclusion was that the integral and the series will either both converge or both diverge. Okay, so then we went to the comparison tests. And the comparison test said, if we're dealing with everything being positive, then 1, if the ANs diverge, that implies the BNs diverge. Okay. Number 2, if the BNs converge, then that will imply that the ANs converge. Okay, this is the go-to one. Now, I don't know how many of you actually figured this one out on the test, or you got the answer from someone who found it somewhere. But the thing that with this one is none of the fancy schmancy tests seem to work on that. You know, good luck trying to integrate natural log x to the natural log x. The limit comparison test didn't work. And the next one, limit comparison test. Okay. And so for this one, all we need to have is AN positive and BN being positive. Okay, so if the limit as n tends to infinity of AN over BN is equal to C, and as long as that's positive, then both series the AN series, the BN series converge or both diverge, meaning they're going to keep doing the same thing. Okay, so that was kind of a useful one, but it really didn't help with this guy up here. Eventually, I'll show you. For those of you that's copied answers down, I'll show you how to do that. Okay, so then we moved into something. Let's see, what came after those? Is it ratio and root test? Ratio. Oops. Ratio test. And the ratio test had something to do, oh wait, then we had the alternating series. Okay, so then we have the alternating series. Okay, and it's the sum, -1, I'm sensitive, -1 to the n, bn, where the bn's are positive. Okay, and so if the sequence bn is decreasing and the limit as n tends to infinity of bn is equal to 0, then the alternating series above, write it again, -1 to the n, b sub n converges. Okay, so it's really not that hard for an alternating series to converge. Okay, and after that, then we looked at the ratio and the root test. So the ratio test said that if I've got any old series, AN like this, if the limit as n tends to infinity of this over this equals L, then the first result, if L is less than 1, the series of the ANs is absolutely convergent. 2, if L is bigger than 1, the series diverges. And 3, if L equals 1, We don't know what to do. Okay. All right. And if you remember how we proved that, it was, we got things involved with a geometric series, like ahead of one for diverging, behind a converging one. And then we had the root test. And the root test is same thing. Have this series AN. If the limit as n tends to infinity of the nth root to is equal to L, 1, L less than 1, converge, 2, L bigger than 1, diverge, L equal 1, we don't know. You have to pick another test. Okay? Okay, so these were the tests that we decided we were going to be, well, not we decided, but, oh shit, hold on a second. Trying to find the Laker game. There we go. Just started. Okay, so these were our, basic ingredients for the test, for the, testing stuff, all right? So then we started to look at power series. Okay, so a power series is a series, the infinite series that's going to have powers of some x minus a. Okay. And of course, the question is going to be, for what values of x does this converge? So we use all of these above tests on these kinds of power series. So the results that we have for the power series let's let f of x be this power series. Okay. Okay. So one of the things that we kind of looked at is that this guy is going to converge trivially at x equals a, because we're just adding up a bunch of zeros. Okay. But what we decided was, and we actually proved this, is that exactly one of the following things are true. The following is true. Okay, number one, it's only going to converge. Slow the action down on this pencil somehow. It's going to converge at x equals a only, or it might be that it converges for every x. It's a real number. Number three, there exists a number r bigger than 0. This is called the radius of convergence, by the way, such that the series Cn x minus a to the n converges for x minus a less than r, diverges for x minus a bigger than r. So basically what we're saying here is that there's not going to be like skipping intervals where, you know, it might, like here's a number line, it might converge for these guys and then one of these and then like that. It doesn't work like that. Okay. So there was a lot of examples in the exercises where he just throws these things in there. So like, for example, for this power series, n equals 0 to infinity of x to the n over 3 to the n. This is just going to be geometric, right? X over 3 to the n. And we know everything about a geometric series. It's going to converge for x over 3 in magnitude less than 1. And as we unravel that, we see that we get -3 less than x less than 3. Now, we don't have to check endpoints for the geometric series. Okay, the reason is because when you plug in the 3 here, you're going to add up a bunch of 1s. Okay, and when you plug in the -3, you're going to be flip-flopping back and forth between 1 and -1. Okay, and from asking these types of things, then we went into the geometric series itself. Okay, so this is how we ended last week. Okay? We were using the geometric series to find power series representations of functions. So like, for example, we looked at the natural log of x, okay, and maybe took its derivative, 1 over x, and then we can insert a 1 and a -1. Oops. 1 minus 1 plus x, which we write 1 plus x minus 1, which has this representation, -1 to the n, and powers x minus 1 to the n. And so then the natural log of x would be the antiderivative of the derivative of the natural log of x. Okay, so it's going to be the integral here x minus 1 to the n, and we just integrate this real trivially. And so we end up with this series, and starting at 0 and going to infinity, -1 to the n, x minus 1 to the n plus 1 over n plus 1. And then if we want to go back, like let's say if we redo the counter, it could like be k equaling 0 to infinity. You want to just make it a little cleaner. Now we're going to have to do the k plus 1 here, and wait, k starting at 1. 1. It's going to be x minus 1 to the k over k. So this was, and then there's a plus c that we figured out, plus c, and then the c went away. Okay. All right, so we were successful in finding a representation for the log of x. Okay, now the natural log of x, oops, and this is all stuff that does not have to be proved yet, okay? None of this, because it's already been established. The natural log of x has this representation. And going from 1 to infinity, -1 to the n, x minus 1 to the n over n, and that has to be n plus 1. And this is true provided this thing that's being raised to bigger and bigger powers is less than 1. So if you unravel that, -1 less than x minus 1 less than 1, 0 less than x less than 2. Okay, so it's going to converge for x going to converge as long as x is sitting in that interval. And because this came from the geometric series, you know, we don't have to check endpoints. You can do them if you want, okay? Oh, wait, since we integrated and took the derivative, we do have to check the endpoints, okay? So since we integrated, it might converge at x equals 0 or x equals 2. So if we plug in x equals 0, it's going to be the sum from 1 to infinity, -1 to the n plus 1, and then it's going to be -1 to the n over n. Now, if I combine that exponent up there, -1 to the 2n plus 1 over n, that's always a 1, a -1. And we know this to be the diverging harmonic series, all of the negatives. Okay, so I guess we're not allowed to use 0. Have 1 everywhere, okay. Can we use 2? Well, let's see. Sum -1 to the n plus 1. Then it's going to be 1 to the n over n. And that's a converging, alternating harmonic series. Harmonic series. Okay, so because we did the integration here, we can plug these numbers in. Okay, now what I was really hoping to get out of you guys last week was this idea that when I took the 1 over x, I can do it as a minus a plus x, which is going to be 1 over a plus x minus a. And then you factor out the 1 over a, and you're left with 1 over 1 plus x minus a over a. All right. Hold on a second. Okay, so maybe this trick will help expand the convergence interval. So we end up with 1 over a times the sum, n equaling 0 to infinity, -1 to the n, and then x minus a over a to the n, which I'll kind of clean up a little bit here. 0 to infinity, -1 to the n, x minus a to the n over a to the n plus 1. And this is going to be converging as long as x minus a over a is less than 1. So that means -1 less than x minus a over a less than 1. Negative a less than x minus a less than a, 0 less than minus a, 2a. Okay, so when a is equal to 1, we get exactly what we wanted. Okay, but let's say we wanted to find the natural log of 3, let's say. So we're going to have to pick a equal to 2 and get the series. Okay. Okay, so now the integral of this will be our series for the natural log. And some of you out there that are programmers, maybe you know where to find these answers. Like, what is your calculator doing? That's what we're trying to figure out. This is one possible approach that you could do. Okay. If I integrate this term by term, I get this sum, to infinity, and it's going to be -1 to the n, x minus a, n plus 1 over n plus 1 times a sub n to the n plus 1, which I'm going to switch the counter. I'm going to start everything at 1. So it's going to look a little cleaner. Then it's going to be x minus a to the n divided by n times a to the n. So we want to approximate what the natural log of 3 is. You're going to have to get into this. Now, I'm old enough to where the calculators that were available to us at the time did not have these buttons on them. Now every calculator does, and I told you I had a guy, I don't know, this guy may have been in he might have been in your pre-calc class, that he could enter in the base, of any logarithm that he wants. Okay, so we had to do tables and stuff like that. But if you needed more precision, so like if you say if a is equal to 3, then let's say we want to figure out the natural log of 5. Okay, so if we pick a equal to 3, we see that it's going to converge as long as x, that's not supposed to be there. That was just supposed to be x. Six, right? And we even figured out that we could use the endpoint, right? With that, okay? Okay, so one representation for the natural log of 5 would be this infinitely long series. Five minus 3 to the n divided by n, 3 to the n, which would be this series. -1 to the n, 2 to the n divided by n, 3 to the n. So if you get sucked back in time and you're around the days when all of these devices were first being built and stuff like that, maybe using the first handful of terms can get you some accuracy. Okay, now as I've maybe shown you here, quite often the series for the one particular function is not unique, meaning that you can manipulate things, and as we did in this problem, okay? To estimate the natural log of 5, we wouldn't have been able to do it with the above series. Okay, so where we are now is, what if we can't use the geometric series result? We always like to use this whenever possible because it's slick and clean, and it's, you know, not a lot of hard work. Okay, so let's suppose that we have a function f of x, which is a C infinity function on some interval. I guess I gotta let the dog in. Hold on a second. Okay. Goddamn Theorem surface going on here. Okay, so what this means is that the function is infinitely many times differentiable. Okay. And f of x is equal to this. Actually, everybody start over. Okay, so let's let f of x equal this series. Okay, now there's a very delicate game of semantics that's going to go on here. Okay. I'm saying f of x, I'm setting f of x equal to this power series. Okay. Now that is a different thing than saying this power series is equal to some function. Okay. That's kind of a little subtle little deal there, but it's kind of important. Okay, so we know that f is a C infinity function on some interval a minus r to a plus r. And it might be that it's the whole real line, or it might be that, the r is 0 and it just converges at a only. Okay. So it's infinitely many times differentiable on this thing. Okay. So if we write down this thing here, to know a power series, is to know the coefficients. After all, how many pieces of information do you need to know a parabola? Well, a parabola is ax squared plus bx plus c. So if you knew a, b, and c, you'd have it. Okay, if you know the coefficients, you know the thing. So if we write this out, write out a few terms here. It's going to be C0 plus C1 x minus a to the first power x minus a squared C3 x minus a cubed. Maybe I'll go out 5 of them. C4 x minus a to the fourth C5 x minus a to the 5. And this sum keeps going and going and going. Well, right now, we can identify that f of a is equal to C0. So that means we figured out what C0 must be. It must be f of a. Okay. And then if we look at f prime of x, that's going to be C1 plus 2 C2 x minus a plus 3 C3 x minus a squared plus 4 C4 x minus a cubed plus 5 C5 x minus a to the fourth. And again here, if we plug in the a, we see that we get C1. So C1 is f prime of a. So now we figured out the second guy. And this trick keeps going. Take the second derivative now. We're going to get a 2C2 plus a 3 times 2 C3 x minus a plus a 4 times a 3 C4 x minus a squared plus a 5 times a 4 C5 x minus a cubed. Okay, now observing here that f double prime of a is equal to 2C2, this means that C2 is going to be f double prime of a divided by 2. Okay, now what are we going to get for C3? If I take the third derivative, then this thing goes away. These guys still have x minus a. But what we're going to get is it's going to be f double prime of a over 3 factorial. If we take the fourth derivative, whoops, the third derivative, if we take the fourth derivative, and I had some German guy at my house one day saying that it's incorrect writing 4 like that. You're supposed to do this. And I said, you know, you Nazi. He was probably right though. Over 4 factorial, okay? And so in general, inductively, we've established the following result. Okay, now pay attention to the order. Okay, so if f of x equals this series, Cn x minus a to the n, then the Cn in general is given by the nth root, the nth derivative of f evaluated at a over n factorial. Okay, so back when we were in pre-calculus, a handful of you that go back that far with me, we kind of talked about this a little bit. Like the factorial function is something that's going to naturally come up in calculus. And here's where we see it happening, okay? Now this is a big if then, okay? So above, we are not saying that, note, we are not saying if f is a C infinity function on some interval I, then f of x equals this series where Cn is given by that. Okay, now for those of you that really haven't been participating, and you probably just turn your computer on and walk away. Okay, and think you can figure it out later. So we're not saying this. Okay, we're not saying that as long it automatically this is going to be the series, or this is how I find it. Okay, but we do have a name for this. Okay, so definition. Suppose f is some C infinity function on some interval I where the A is right smack dab in the middle of I. And we call the series sum n equaling 0 to infinity of the nth derivative evaluated at a divided by n factorial, because that's what we found what the CNs must be, to the n. We call this the Taylor series. Of f. Okay. Now, the big $1 million question is, when does a function equal its Taylor series? And way back, gosh, it goes clear back to 180 stuff. There's an exercise showing you that some function is infinitely many times differentiable. But it's a really tricky problem. Okay. All right, so more to this definition. If f of x equals its Taylor series, and that's a big if, write it down again, n equals 0 to infinity, fn of a n factorial x minus a to the n, then we say f is analytic. Okay, so this is like the crowning achievement, being analytic. Okay. So it's harder to be differentiable than it is to be continuous, right? I mean, this is continuous, but it's not differentiable right there. It's harder to be twice differentiable than one times differentiable. So if you keep playing all that out, infinitely many times differentiable, well, there's one better than that, and that's when the function is actually equal to its Taylor series. Okay, now this gets named after Brooks Taylor, circa, I don't know when. Let's see, maybe it'll, I can look it up in the book. I mean, I could look up on the phone. Hold on a second. What is that? Brooks Taylor. I think I got his name right. No. Math guy. Maybe his name isn't Brooks. Maybe it's a book. Maybe in the book somewhere. There we go. There we go. Brooke, not Brooks. Brooke. Okay, so he's 1685 to 17. So he's late 16, early 1700s. Okay, now this didn't get named after Brooks Taylor because of all of this that I just figured out. Okay, I mean, any moron could do this. I mean, I did it. Okay, why Brooks Taylor's name gets attached to this, it has to do with a remainder theorem. Okay, now a special note here: if a is equal to 0, then the series 0 to infinity of the series, the nth derivative evaluated at 0, n factorial x to the n. This is called the Maclaurin series. Of f of x. And again, it wasn't just because, hey, look, if I stick a 0 in here, it looks kind of cool. Okay, so Maclaurin is roughly around the same time, a little younger, and died like 15 years after. Okay. Now, what these guys were doing was kind of a similar thing that what James Gregory had been doing at the time. If I look up James Gregory, mathematician. So he's 1630 to 1675. Okay, so he predates these guys a little bit as well. Okay, and he was looking at the kind of stuff that we were investigating yesterday. Long before Newton and Leibniz came along, people were figuring out these derived functions from other functions. Newton just kind of organized all of this, and he actually established a few results. One of them we'll look at today, or maybe not today, maybe tomorrow. Okay, but it's these guys that were, you know, really pushing the development of calculus this way. Okay, these non-polynomial functions seem to sometimes have infinitely long polynomial representations. Okay, now put yourself back in the day in their shoes. Okay, they didn't know how to calculate the natural log of 5, nor did they know how to estimate the square root of 7. You fast forward, you know, 300 years or so. Do we know how to compute the natural log of 5? Did we get that smarter? Do we know what the square, do we know how to get the square root of 7?
No.
No, we don't, man. We don't. We have devices that have been programmed to do this, but we still don't know. Okay. So I've already, you know, we know that this natural log of 5 one, we have a series for this. Okay. What we need to work on are finding series for, you know, to help us with this stuff. You know, if we're navigating at night, we might want to know what the sine of 2 degrees is. We don't have a calculator to do it. You know, shit, watch Apollo 13. When all hell breaks loose, these guys are on their slide rules. I'm actually old enough for, I learned how to operate a slide rule and an abacus. So what do you think about them apples, huh? Okay, so these are kinds of functions that would be of big interest to us. All right. Okay, so if f of x actually equals this, k equaling 0 to infinity, the kth derivative a over k factorial x minus a to the k. We use these Taylor polynomials. This would be the nth Taylor polynomial. And it's going to stop at n. And it's the same thing in here. Like so, to estimate f of that x. Now, if you thumb back in your calculus book all the way back to chapter 3, and I'll do that right here. Actually, this book doesn't go back to chapter 3. Fine. Well, anyways, when you go back to there in the end when we were talking about linearization, at the end of that chapter, there's like a problems plus type section where he starts talking about these nth Taylor polynomials. And let me get, it's so important. I need to show you where it is. And by the way, this is going to be an interesting exam because finding these series, does this book go back that far? Yes. When I asked certain, over the last few years, I put certain types of problems on the take-home exam, and the answers that come back are, I can tell they were plugged into Wolfram or something like that. They don't actually give me a series. You know, I'm going to say this several times. When I'm asking for a series, you have to give me the entire series, not just the first 5 terms and say dot, dot, dot. Okay. Okay, so back here at the end of chapter 3, I think that's where it was. Nope. Yep, there it is. So it's at the after the exercises in section 311, laboratory project, Taylor polynomials. So my math and my physics major, Eduardo, and my physics guy. Who's the physics guy? Are you here today? I really strongly encourage you to go back and read that carefully. Of all of the stuff that we're doing this semester, this stuff is going to be by far the most challenging. And whether we're doing it online versus regular class, your level of understanding of this is not going to be indicative of how, you know, what your grade is. Like, you might get an A and just not have a clue on what the hell's going on. Okay. When I went through this the first time, all of this was new. We hadn't done anything in my high school calculus course like this, these infinitely long series. And I did not fare well. Matter of fact, I had to repeat that class. I had other stuff going on, of girlfriend problems and stuff. But the second time through, I nailed it, kind of. It wasn't until I had to start using it later in physics that it really started to sink in. So the more exposure you guys can get to this, the better. Now, my professors didn't point this stuff out. Read this. This is why doing this. It was just a machine. Do this, do this, do this. The guy that I had for this class, Professor Banks, the British guy, kind of like Mr. Banks from Mary Poppins. And he really sucked. And then, but whatever. Okay, so this is what we're going to use to estimate. Now that's the big if. Okay, so before we get into Taylor's theorem and start trying to establish what's analytic and what's not, and the method. Okay, so the following functions are all analytic. Okay. So this guy, which we've been using, has this power series representation. Okay. This is just on, this was analytic by default. Okay, there's nothing that needs to be shown here. However, when we start getting into these guys, e to the x, sine x, cosine x, nth root of x, all of this stuff, all of these guys are analytic. Okay, so we're going to develop the series for these things. And then when we do Taylor's theorem, maybe we'll take a stab at proving that e to the x or something. I realize who my customers are, but since I do have one official math major in here, I need to do stuff for him as well. Okay, so let's start with e to the x. Okay, so let's find a Taylor series for e to the x. Okay, so let's, pick A as the center. Okay. Now, this is so easy. The nth derivative of e to the x is just e to the x, right? And so the nth derivative of e to the x evaluated at a is e to the a. So this means that e to the x is equal to this sum. And starting at 0, going to infinity, and it's going to be e to the a divided by n factorial x minus a to the n. And the Maclaurin series, if a is equal to 0, if we select a equals 0, then we have this series. N equaling 0 to infinity x to the n over n factorial. Okay. Now, this is a result that you probably want to memorize. Okay. Now, there's a whole bunch of stuff that we're going to be looking at here, but at the end of the day, there are 4 series that you're going to want to remember. This guy, and remember, he's valid only there. The e to the x one, and the sine and the cosine.
Can you go back up a bit?
Like to there?
Yeah, just there. I just needed to get that. Okay.
And did any of you guys ever see this movie where this kid reads in an encyclopedia or something, I don't know, how to make an atomic bomb, and then he breaks into this government lab and steals some nuclear material?
Isn't that the Venturing? What's not the Venturing?
Well, the John Lithgow, he was like the head scientist.
Mm.
So did you guys see the movie Daddy's Home too?
Yeah.
Okay, so Will Ferrell's dad?
Yeah.
Okay, so he plays the head scientist in this movie. And then they're trying to disable the bomb, dismantle the bomb and stuff like that. And there's a
Manhattan Project?
Yeah, that one I was going to
Is
say.
that what it is?
I literally Googled it. It's about a high school student who decides to construct an atomic bomb. It's about the
Yeah.
Manhattan Project, 1986. It looks like John Lithgow's in it.
John Lithgow, yeah. And so there's a scene in the movie where he talks about how, okay, so e to the x converges at like what? And the kid goes like 1 over n factorial. And, it's some weird reference that hardly anybody gets except me, but it was even built into the movie. And he made a comment like, wow, you're pretty smart, kid. You should do something with it. Did any of you guys watch Hiroshima thing last night?
No.
Yeah, it was a big old 2-hour special. I'm probably going to watch it again. I lived right across from my grandparents. So this show last night was about the development of the bomb and the atom bombs, the nuclear bombs and stuff like that. And on that Manhattan Project, right across the street from Grandma Jane's house in Point Loma, on the ocean side of Point Loma, there was this guy, Norman Hicks, and he was a physicist on the Manhattan Project. Unfortunately, he passed away before I got smart, because man, would I have loved to have, when just as a 19-year-old kid, knowing stuff. I think he died when I was like 12. Just to pick his brain about, you know, I mean, he was there making the thing. It's like amazing. Okay, so if we use the ratio test on this, which we've already done, I snuck this into you guys last week. I said, hey, you tell me what values of x this converges for. Go ahead, look back in your notes if you were taking notes. I did it. We found that this converges for all x in R, okay? Now, if you guys remember a little bit, when we were doing the linearization stuff, if we want, this is the square rooting guy, okay? If we wanted to compute the square root of 3, we would probably use the linearization at 4, right? Because if you remember how that worked, you pick a spot where the derivative is easily evaluated, okay? But the further away you move from 3, see, look, I'll show you. So this value on the y-axis here, this is the actual square root of 3, okay? And if we're going to do the linearization at 4, you know, the linearization is giving us a tangent line. Now let's see if I can draw a nice tangent line here. Kinda. Okay. So the 3 is going to map up to the tangent line right there. And so that is the linearization at 3. Okay, now you see that the values are pretty close to each other, right? But the further away you get from the number 3, the worse the approximation becomes. Okay. Now, a similar type thing is going to be happening here. If the e to the x series converges rapidly for any x, okay? But if I wanted to maybe compute the number e to the 18th power, it might be better to use a different value of a, okay? So I'm going to kind of go through what the way I understand how this is working later, okay? Like what I think is going on inside your calculators. And again, those of you that are maybe in the business, maybe Brian, maybe you're a programmer, right? Maybe you would know where to look or who to ask. You know, okay, what is the calculator doing? Like, we're going to find series for all these things. We've already found a series for e to the x. We found one for the log. We'll do sine and cosine right now. Let's let f of x be the sine of x. Okay, and we're going to use a equals 0. Okay, so f of 0 is equal to 0. So f prime of x is cosine of x, and f prime of 0 is 1. Okay. Double prime of x is negative sine x, and f double prime of 0 is 0. Triple prime of x, negative cosine x, and so f triple prime of 0 is negative 1. And then after this, the list repeats itself. Repeats. Okay. All right, so I've already told you that sine x is analytic, so we're just going with that assumption. And this may have been what some of the early guys like James Gregory and Colin Maclaurin were doing. But it was Brooks Taylor that gave us a tool to decide whether or not a function is actually analytic or not. Okay, so for this guy, the nth derivative evaluated at 0 is not equal to 0 for n being odd, and fn of 0 equals 0 if n is even. Okay, so apparently only odd terms are going to show up here. Okay, so now I'm going to write this out like this. Okay, so let me write it like this. Okay, so the sine of x. Okay, so it's f of 0 divided by 0 factorial, right? Times x to the 0 power, okay? And then it's going to be plus f prime, f1 prime, okay? So that's going to be a 1 over a 1 factorial, and then there's an x. And then there's going to be a 0 over 2 factorial x squared. And then there's going to be a negative 1 over 3 factorial x cubed. And then there's going to be a 0 over 4 factorial x to the 4th. And then it's going to be a 1 over 5 factorial x to the 5th. And then plus a 0 over 6 factorial x to the 6th. And then a plus negative 1 over 7 factorial x to the 7th minus plus da, 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 da. Okay, so all of the even things are zeros. So if we want to write this as a sum, it would be n equaling 0 to infinity. Now it's going to alternate back and forth between 1 and negative 1. Okay, so we'll put the n up there. Now the only powers of x that are going to show up are odd powers. So this would be 2n plus 1. And when n is 0, we have to get 1 for the exponent. And then we divide by that exponent factorial. Okay. And so we just figured out that the Maclaurin series for the sine of x, 0 to infinity, negative 1 to the n, 2n plus 1, 2n plus 1 factorial. And this is valid. You guys will use the ratio test on this one and show that it's actually valid. Okay, now you notice that this is an alternating series, right? So we have results with alternating series that say, I just want to remind you of something here, because this is going to bring up an issue. Okay, so for an alternating series, the remainder thing, if you remember, was less than or equal. It could be no bigger than the n plus first guy. Okay, so the question that naturally comes up, if I go in red here, this term right here, I mean, not this term right here. What term is that actually? It's actually the fourth term, right? 1, 2, 3, 4. But it's the second term here. Okay, so we're going to need to get into this. Maybe we'll do an experiment to decide if we want to use the alternating series result. Maybe what we need to do more of is this. R sub 2n would be less than b sub 2n plus 1. Because at least we have those guys. Okay, so anyways, more on that to come. Okay, so we just did all the heavy lifting with sine. Now remember that the derivative of sine is cosine. Okay. The result from last Thursday said we can term by term take derivatives of these power series. And so this is going to be -1 to the n. The 2n plus 1 is going to come down, leaving me 2n here. It's going to cancel with the first 2n plus 1 in that factorial and leave us with this. Okay? And so what we've got is now the cosine series. -1 to the n x to the 2n divided by 2n factorial. Okay, now we've been told our whole lives that cosine is an even function and sine is an odd function. Converges for all x and r. Let's write the sine guy down next underneath it. Sum 0 to infinity, -1 to the n, 2n plus 1 divided by 2n plus 1 factorial. And again, it's converges for all x and r. Okay, so a series for the sine of x, it's going to be x minus x over x cubed over 3 factorial plus x to the 5th over 5 factorial minus plus. Now, back when we did the linearization in chapter 3, we found the linearization with a equals 0, and at a equals 0, we found that the linearization, I like to put a equals 0, of x is just x. Now, the reason that he goes into the story in the Taylor polynomials after you do all that is because he's saying, well, look, this is just one approximation. It's been very recent discoveries that scientists and astronomers have found out that there's a lot of interesting stuff going on Pluto, which is very, very far away. It has some heat source that you can't quite figure out. Its moon, Charon, follows it along, and it looks like they share a magnetic field, and I don't know. You got to watch it on the Science Network. But in any event,
Real quick, is Pluto the one that's not the planet anymore?
They concluded that it's a planet again.
That's Pluto.
Oh, wow. Man, they just can't make up their mind, huh?
They really can't make up their mind.
But wherever you want to classify it, it turns out because of, you know, having the Hubble telescope and this, I mean, we're now going to be sending, I think something is already on its way or it's being planned to go to Pluto. Pluto has some weird stuff going on, but in any event, my point is this. If we were going to approximate the sine function with a polynomial, sine x is almost equal to x. And this is for small x. Okay. Now, the reason that you're learning all of this stuff is because not because of how to do this. Like, yeah, our calculators can do all this shit, right? But it's when we have differential equations and like the pendulum problem is the classic problem. In the pendulum problem, we want to find the equation of motion of the ball going, swinging back and forth. Okay. The parameter here is this theta. In the differential equation, there's this annoying sign of theta that doesn't allow us to solve the problem directly. When you can't solve the differential equation directly, you have to guess it's a Taylor series or a Maclaurin series. That's where those Bessel function things came from that we talked about last week. So if we were sending our thing to Pluto, we don't have enough fuel to keep the fuel on the whole time, unless we want to go nuclear. But even then, you know, the amount, well, who knows what they sneak up there in space and don't tell us. That's what I'm waiting for Trump to do. Like, once he decides that let's say he loses. Do you guys think he's going to lose in November?
Oh,
Okay, well, let's say he does. He's the kind of guy that's going to blab his mouth and go, oh, yeah, well, I know what's going on at Area 51. And let me tell you about what we got up in space right now, pointing at the Chinese and this and that. He's that kind of guy, you know? So who knows what they put up there. But in any event, if you need a better estimate or approximation, you probably want to go out a few more terms. Okay. Okay, now let's kind of look at some interesting features here. If I remember from right angle trigonometry, which I had to teach myself, if this is x, then this angle up here is pi over 2 minus x, right? Because in flat Euclidean space, all angles on a triangle have to add up to 180. Now, if you put a triangle on a hyperbolic surface, then the angles add up differently depending on, like, if you go halfway around the world and then go straight up and then go back down, all of these are right angles, right? You know, start here, start at the equator, go all the way up to the exact North Pole, and then take a bearing of due west and go down. And to you, you're walking at a right angle, right? And you're coming down. Okay, so the measure of an angle of all the sum of the angles on a triangle is relative to where it lives. Okay, now remember this, that the sine of x, that's the same as the cosine of the other angle, right? Pi over 2 minus x, which is the same as the cosine of x minus pi over 2, right? Because cosine's an even function. Since this series above converges for all x's for cosine, I'm going to plug that into the cosine sum. 0 to infinity, and then it's -1 to the n, x minus pi over 2 to the 2n divided by 2n factorial. So if you were having to estimate the sine of x where the angles are kind of close to pi over 2, it would probably be better to consider this series for the cosine of x minus pi over 2. Now notice that we're saying this is what sine x equals. So this is yet another series for sine x. Okay, it's not the standard one. And we can play games with this with cosine as well. Okay. Okay, so the kinds of problems that he's got in the exercises are things like this. You know, find the Maclaurin series for the function e to the negative x squared. Okay, solution. We know that e to the u is the sum 0 to infinity of u to the nth power n factorial, and it converges for all values of u in the real line. Well, negative x squared counts, so e to the negative x squared would then be this series, 0 to infinity, negative x squared to the n over n factorial. And I can clean that up a little bit by saying it starts at 0, goes to infinity, and it's going to alternate negative 1 to the n, x to the 2n, divided by n factorial. Okay, so now at least we can maybe do some numeric integration. If I wanted to integrate from 0 to 1, e to the negative x squared dx, there is no antiderivative for that, but we can integrate the power series, okay? And if I integrate the power series, it's going to be x to the 2n plus 1 divided by 2n plus 1 n factorial evaluated at 0 and 1. And when it's 0, it's nothing. So this series represents the integral. Negative 1 to the n, 2n plus 1 n factorial. And because of that n factorial, it's going to converge very rapidly. Okay, now we're never going to know the true number here. But because it's an alternating series, maybe let's see if we can find an n such that the Rn is going to be in magnitude less than that. Okay, so the solution here is we set Bn plus 1 less than 0.00001. Okay, so Bn plus 1 is going to be 1 over 2n plus 3 n plus 1 factorial less than that. So then if you remember what we were doing last Thursday, needs to be bigger than 10, 100, 1,000, 10,000, 100,000. 10, 100, 1,000, 10,000, 100,000. So then you just start trying some stuff. N equal 4. I don't know if my Apple calculator has the factorial, but yep, it does. Okay, so 5 factorial times 11. Not big enough. N equal 5. We'll go 6 factorial times 13. Still not big enough. Maybe we got to jump to N equals 8. Let's go to there. Okay. 9 factorial, and that's already massive. N equaling 6. 7 factorial times 17. N equals 6. 12 times 16. 80,000, so it looks like it's N equals 7. So for N equals 7, I'm usually better at guessing than that. Then times 14 times 17, and that's 685,000. Okay, so for this guy, the integral from 0 to 1 of e to the negative x squared dx is approximately equal to the sum, k equaling 0 and stopping at 7, and it's negative 1 to the k, 2k plus 1 k factorial. Now you can add up all 8 of these numbers, and you guaranteed that, okay, whatever that is within this tolerance right here of your guy, even though we don't even know what the real answer is. Okay. Now for this one in particular, these are very important ones to get because, as I've told you before, this function scaled where they put some number in front of it here, e to the negative, then they put another number here, and then the x squared where the sigma is positive, and there's probably something else over another number. But in any event, that is the graph of the e to the negative x squared scaled to have an area 1. And if you tried to get into, let's say, UCLA Medical School, after you finish your bachelor's degree, you're going to apply, take your MCATs. They're going to have a grade point average for you, and they might accept the top 2%. So everybody's going to get a number. And the central limit theorem in statistics says that the distribution will look like this. If you just reach your hand in, grab out. So of the top 2%, that means you want some cutoff score over here, C sub 0, to where the area in here is 2%. Okay. Same kind of thing happened to you out of high school. If you wanted to go to UC Santa Barbara, you had a number and they're going to take the top, I don't know what the Board of Regents does now, 10%. They probably have special rules. Any foreign student can come because they're really hard up for money. Okay, but for this kind of stuff, this is why you would need to know these numbers. Okay, so we will kind of end this here because I don't want this to get too carried away. The next thing is the binomial expansion. So this is the thing that Newton figured out. So we'll talk about this tomorrow. So what I want you to do is catch up the rest of this section. We will finish tomorrow. I've learned that if I go, there's only so much I can do here.
Professor, real quick, is there any in particular that you want us to check out on for this section?
Any problems?
Yes.
Okay, so in exercises in 11.10, he's asking you to find a Taylor series centered at the given value.
Mhm.
Exercises 5 going through 21 or 20.
Okay.
They're, you know, some of them are easy, some of them maybe not so much. Okay, now we haven't done the square root yet. Okay?
Oh, okay.
And for that matter, any of the roots. So the root thing could be handled maybe by the binomial expansion tomorrow, but you know, we'll go through it. Yes, that's in the version of the book that I'm looking in. Your numbers might be different, but in 11.10, there's just this batch of these things.
Okay. So we just don't do the squares or the roots. Just wait until we.
Well, you know, number 20 is the square root of x.
Oh, okay.
So if you want, try to do that on your own. And then tomorrow when I'm doing it, we'll see, you know, how you did.
Okay.
You know, this material, I mean, if we were in a normal class, I'd stop right now as well. Okay, there's only so much of this stuff that's digestible at one sitting. There's some of you in here that I know, or this is your second time through, and so it's a little easier, but I bet you that this was the hardest part of your experience. Anyways. Okay, so tomorrow we will finish 11:10, and then we're going to get into Taylor's theorem. Now he does a bad job of butchering the Taylor result in the book. So I have the statement of the theorem and the real proof, or a suitable proof, that we will be using. It's basically going to tell us if we stop at Tn, how bad could the rest of it be? Like how big could that remainder piece be? And it has, and let me see if I can find this thing before I put the book away. Way back in chapter 2, I think it was, he has the function that is infinitely many times differentiable, yet not analytic. So let's see. There's a change. I'm in section 3, 3, 4. 5 is the chain rule. 6 implicit. Okay, 7 is higher derivatives. It's got to be in here. So not there yet. Where does he put this thing?